Alright.
Oh, well, yeah, that one then.
So, we started talking about colligative properties yesterday, not yesterday, 2 days ago. What were colligative properties dependent upon? Oh boy. The number of solute particles, because we're talking about how solutions properties are different from solvent properties. And how they differ is dependent upon how many solute particles you have dissolved. Not what the solute particle is, or what it's made of, it's how many. Okay, then we talked about its effect on a few things. We talked about its effect on the boiling point and the freezing point. We also talked about its effect on osmotic pressure and osmosis. We talked a couple days ago about dialysis and what goes on with that. Okay, so we're going to finish talking about that today with reverse osmosis and something known as ion pairing. Okay? So what was osmosis?
It's the flow of solvent into a solution of a cement permeable membrane.
Okay? The flow of solvent into the solution. So what do you think reverse osmosis is?
Solution of the solvent.
Yeah, the solvent of the solution into the solvent.
So it's what was the solution is under pressure?
Yeah.
Okay. That's that thing. Okay.
So we had our semi-permeable membrane, and we said this was the solution, and we said this one was the pure solvent. And under normal osmosis, what you would see is the solvent going like that, or the net change, right? Well, reverse osmosis is when you take a pressure greater than the osmotic pressure, because remember, osmotic pressure is the pressure you would need to push down here to maintain equal levels, correct? Okay? If you exert a pressure greater than the osmotic pressure, what you can essentially do is force solvent this way. Make sense? Okay? I don't think that's an overly difficult concept to grasp. Okay, now we have kind of talked about this, but we're going to put a variable to it, or a math concept to it. We talked about colligative properties dependent upon how many solute particles you have, and then we said it becomes important when you deal with covalent versus ionic. Why was that a thing?
So ionic breaks apart.
So
it doubles the moles or triples the moles.
However many it breaks up into,
Yeah.
right? Okay? So we can figure out how much more an ionic compound is going to impact than a covalent by looking at how many more particles it will break up into. And they refer to this number, or this whole number multiple, as I. So if I have CaCl2, okay, it breaks up into how many particles?
3I.
It breaks up into 3 particles, so I is 3.
Oh, okay.
And what they're going to do is they're going to put the I in front of this equation, which we've already dealt with, yes? Okay? And if it breaks up into three times as many particles, that just goes immediately into the equation. You don't worry about changing anything before you put M in. Does that make sense? So if I find M of CaCl3, the molarity of this to be 3 molar, I would just plug 3 molar in, and then if I is 3, put the 3 in for I. Does that make sense? Yes?
So at the same molality, if it broke up into more, it would have a higher automatic
Molality?
yeah.
Okay.
At the same molality, would it have higher osmotic pressure if it breaks up into 3 instead of into 2? No matter what.
Like if I had a 3 molar calcium chloride versus a 3 molar sodium chloride? Is that what you're referring to?
Yeah.
because this breaks up into 3 particles and this breaks up into 2 particles.
Yeah.
And what was the last part of that you said? It makes it higher or lower what?
For osmotic pressure, would it always be the one that breaks up into 3?
Yeah.
Okay.
Because the more particles you have, the more it affects all of those colligative properties.
That's the one I couldn't figure out, thank you.
Answer.
Cheating, I asked him for help.
There was a cheating.
No, he did.
Okay. Now, where does this come into play, and is this always the case?
Wait, wouldn't that one be 2 rules? Oh, they just erased.
What are you asking?
Why is it 3?
Because that's the concentration of the whole thing.
That's not the.
That's
you're
not-
saying it's the I. You're saying
This would be what it would be after you broke it up into its particles. And this would be 6 after it breaks up into its particles. Make sense? Okay. And here's another way to figure out your temperature change, but I don't know if you'll see that too much. Okay, I want to talk a little bit about ion pairing. So let's compare the I of glucose. What is the I of glucose?
1.
1. Okay? And let's compare it to the I of sodium chloride. What's the I of sodium chloride? 2. So if we were to take these guys and put them in a solution with identical amounts, we would expect the boiling point elevation or the freezing point depression to be the same, half, double. What would you expect?
Double. Full. Double.
Freezing point will be lower than
Okay, yeah, you're right. It does depend on the molarity. I should have made it clear that they have the same. So let's say I got 3 molar of each of these guys. Okay, you would expect, right, that the freezing point elevation, for if it had sodium chloride in it, would be double that if it had glucose in it, right?
But then you talk about the reason why is because it's less water per the total. So there's less water particles per the whole thing. So glucose is a lot bigger though. Wouldn't that take up more space, or just not enough that it would matter?
Well, you also got to think about surface area being able to surround more particles versus 1 particle, and that as well. I'm not 100% sure how much that plays an impact.
Okay.
Okay, so the point I'm trying to make here is when you actually figure out mathematically, figure out how the change in the boiling point is affected, not H. I'm so used to writing change in H. Okay, so let's say we found the change in the boiling point when it's got glucose in it to be 0.15. We would expect the change in the boiling point for water, if everything else was the same, to be what? 0.3. Okay? Well, it's not actually perfectly 0.3. What they found out is the boiling point elevation when you put sodium chloride in versus glucose is about 1.87 times greater. So close to 2, but not quite 2. Okay? So they had to come up with, okay, why would this be the case? And the answer is ion pairing. So here's what basically ion pairing is. Ion pairing is, it's possible that if you dissolve table salt in water, that you still got positive ions and negative ions in solution, correct? Is it possible that some of those positive ions and negative ions could, in the words of your chemistry book, aggregate?
Yeah.
What do you think that means?
Collect, come together.
Yeah. there's my reader right there. I can always trust him to have the right words. That's a good thing. Okay? What that simply means is there's always going to be a small amount of clumping, if you will. Okay? Well, if you've got a few particles clumping, is that going to diminish the amount of total particles you have? Yeah.
Yeah.
Yes, it will.
Yeah.
Just like, these things not breaking apart and they're always clumped as one whole thing. It's the same idea. Now, let me see if you guys can figure out why this would be the case. So I'm going to write this down because I want you to do this.
Also, that definition is number 20.
What?
Number 20, question 28 is, what is ion pairing?
Oh.
That's why I put my homework down.
I want you to write this in. Why there is less ion pairing when it's dilute, but I just gave you the answer. So go ahead and get this in.
I mean, it's just like pressure when volume is decreased and they're just closer together or farther apart.
Sorry, say that again.
It's just like the change in pressure when volume is changed because like they're closer together, farther apart.
Yeah.
Okay.
I mean, ultimately, when you've got a dilute solution, you have less particles in the solution, correct?
Yeah.
And due to sheer entropy and the fact that things want to be in its most random state as possible, that would mean that those particles would be further away from each other, correct?
Yeah.
Now, and if they're further away from each other, they're less likely to what?
Trapped like magnets. Or
Yeah, they're less likely to pair. Should be given that. Okay? So, ion pairing is this idea that ions, because they're attracted to each other, a few of them could aggregate or pair together, thus diminishing the overall amount of particles, and thus not having as much of an impact as you might think as it would.
Usually overcome by just warming up the solution. Would that prevent it from happening or make it
I don't know
less?
the answer to that. I don't think it will talk about that.
Okay.
Maybe.
I mean, it makes sense because they're being moved further, so they can't.
Yeah. They're moving faster, but then, yeah, maybe
Again,
I
they'll
don't know.
pass each other more moving faster. So I don't know.
yeah, you add a few more variables into the equation in that situation. Okay, let's do a problem with this.
So what's the first way?
I'm gonna hand it to some more students.
So
What is it?
it's a
It's up to
guy-
you.
You already have braces.
Perfect, it's perfect for you. Just show how to brush your teeth.
I know, I've had phrases.
Is this yours? Eating habits.
I have them eating.
How to be a happy patient. Are you a
No,
sad patient?
No one is happy when they get braces, they're painful.
Well,
So-
maybe this book is for
There are
you.
no happy patients with braces.
Ah. Emily, this will teach you how to put your headgear
Way
on.
up here, back here.
I didn't.
Yeah.
Like,
It's
this is
tape on
yours?
Way up
No.
there, and then
Well,
they tighten it, and then
But
they
where
work
my
out of
teeth
it.
got pushed back.
I have
The other guy put in the face.
Yeah, that always.
We're a metal face.
They got yanked down.
What?
Ryan Cricket got stuck there for years, and so they.
Mine was
they-
back, you know, I got
Yeah.
beat down by floors.
Sorry,
Then I had to have a roof.
No.
I had that back here.
It's the
Well,
worst.
they had,
It's like-
they,
You only have to wear it at night.
they had to
Yeah.
expand
Well,
all
it has
the
like two
outwards.
Did you ever like
Put it
try
in
to?
and then put it back.
Oh, really?
I pretended
Yeah.
like it.
I had
pretended
rubber
it was
bands
hurting
and
me, so I
tape
didn't
it,
have to
so
wear it.
like it hurts.
So you like never wore it?
I had like nightmares as a kid, like you know, like in Finding Dory, like how the little girl wore headgear like every day. So I was
Yeah.
like, what if I grow up and I have to have headgear and then I have to wear it every day to school and then when I grew up and I had headgear, I'm like freaking out. Like, no, you only wear it at night.
No, I knew it. I was talking about work during the day.
Oh,
Because she
no.
didn't want, because she wanted to go past him, so she didn't go
That's the.
I don't know why she did it.
Well,
My mouth would hurt so bad every morning.
Then again,
It was like the
if
top of your
you,
teeth.
if you're at home for most of the morning, you can just
That's
take, you
true.
can wear it in the morning, take it out.
They're like, try putting it in as soon as you get home after school and then you go by fast. I'm like, yeah, I won't get home by 10 o'clock.
I have a friend from
practice
school.
and friends.
All the school work in like 2 hours, he just does whatever he wants the rest of the day.
alright, let's do this problem. And the observed osmotic pressure for a 0.1 solution of whole iron ammonium sulfate. I don't even know how you'd say that.
It's thin.
At 25 degrees Celsius is 10.8 atmospheres. Compare the expected and experimental values for I. So what would be the expected I?
3? No, 2, 5.
Well, 2, 3, 4, 5. Which one is it?
5, because it's 2 of each of the polyatomic and then the iron.
It's 5, yeah. Okay, so we need to figure out the
Literally giving us the polar mass. I need to start on that.
what do we need more mass for?
I think it's,
No.
What
other
you
bit?
need, oh, but,
Oh, yeah, body water.
literally gives you moles.
What other information do we have?
You know the moles
Pressure.
of,
Moles. We don't.
And
of
molarity.
heavy.
Molarity.
And
We know the molarity pretty good.
in the molarity, we can help you find moles like
Okay.
that.
Alright. What else do we know?
Temperature. Which is, yeah, it's 298.
What else do we know?
It's already an 18, right good there.
Hey, that's a pretty easy problem.
That's sustained.
No one's supposed to be hard. You only get 40 minutes in class. You have like 7 hours after class.
That's funny.
That's a lot of
That's funny that you think that I have that much
The
free
only
time.
thing I do is advanced chem.
Pretty much.
Yeah, it's like all my homework.
Why not? I know you guys really love being in class. Why wouldn't you love doing it outside of class?
I didn't even have a 3-day weekend.
I don't have
Because
kids.
it's hard.
I spent 2 days of my 3-day weekend somewhere else away from home without time to do homework.
Really?
I went to Clear Lake, the way meltdown at IRBC.
Okay, why don't you solve this problem then?
That's why.
Didn't it take like an hour and a half?
My handwriting is so bad though, I cannot do it on a sunset.
Wait,
Excuses, excuses.
why was that
I
unexpected?
just took too long study all of a sudden, that sounds good.
What?
Why was that unexpected?
How many particles breaks up into? 1, 2, 3, 4, 5.
You never write down what one
Anyway.
You don't really.
Wait, oh, yeah.
No,
I know it is.
08206.
That's what I was trying to say. Hold on. We're done?
You should just like round up though.
I think about a lot of games this week.
Isn't it supposed to be molality though, not molarity?
When we be like
equation?
5 weeks instead of 8.
I don't think I ever joined, I picked the wrong one.
44.
Has Northwestern offered you a scholarship yet?
Yeah, they're making it like the official thing or whatever. I'm going out of my
Oh, really?
yeah.
Who do they play?
Hastings or something. Is that who your sister hit the shot?
Yeah.
Hastings?
Yeah. I had one of my better games against Hastings, too.
That's point.
I put point on it.
So is it Dark Galen College that has offered you?
No, them and Northwestern and Briarcliff and Morningside and
So you don't like that?
yeah, I've already like kind of and Grayson.
Which one offered you the best scholarship?
It was all like full tuition.
So everyone, all the teams have offered you pretty much the same
So, yeah.
thing. Grace.
There was a guy that came to, I think, I don't know if he came to watch you or something, or was it because he's the girls coach, but he came to a random game.
For the
And-
girls team.
Yeah, he talked to me afterward, he was like, yeah, he was like making these.
Yeah, we only win 4 games a year,
He's
but
like-
you would be a difference
They're
maker.
good for a guy.
He's like-
actually.
You get these like
I think I got
elite,
them last year.
elite Nike
Oh.
tags and shoes, and there's like, and you get these shirts, and he was wearing like a Graceland like 5-fish shirt. Like, nice.
Great. How about the college education?
Yeah,
Okay. Anyways,
they're so funny.
I'm assuming you guys got what? 4.4. Yep. And why is that different?
It's 0.6 less.
No.
Because it's concentrated enough that the ions are coagulated.
What's happening here?
Hey, what's that word again?
Aggregate.
I said everyone did.
Coagulating?
I made up that
I
one.
did that.
Aggregated. Okay, the reason why that's lower than what you would expect is because of ion pairing. Essentially what's happening is ions are pairing up and acting as one molecule instead of multiple molecules. And we know from a colligative property standpoint, that is important. Last thing, you guys remember these? This is 100% for you.
Yeah.
Tyndall effect?
The Tyndall effect and colloids.
I do remember that, yeah. It's like, it looks murky. And the light scatters and it would shine light through it.
Oh, yeah. Like a laser.
So pretty much what the Tyndall effect and a colloid is so colloids are like halfway, or I don't know if it's like perfectly halfway or not, but I like to view it just as halfway in between a suspension and a solution.
It can be dissolved in their big particles, is that what it is?
Well, technically I don't think they actually are dissolved, but you can't see them. I don't know, it's kind of goofy. So,
You can, when they have evaporated milk, you can remove the quote-unquote solvent.
So colloids are right in the middle, and really what separates, you can tell what it is by the Tyndall effect, which we'll get to in a sec. But the only way to truly know if it's a colloid is particle size. These have the smallest particles. These have large particles, and these are in between. And I think there's a range, just like 1 to 1,000 nanometers or something like that.
1 to 1,000 millimeters.
Yeah, there it is. So what ends up happening is the particles are somewhere in between the two, that it almost has properties similar to both of them, usually closer to solutions, and that usually you cannot tell the difference between a solution or a colloid very well. Sometimes it looks hazy, but most of the time you can't even tell.
All of it's a colloid.
Mhm.
So it's dim. No, it's not.
We don't know what Jello is.
We don't know. It's goopy.
It's goopy? Okay, so I'm sure there's a picture. Let's see if we can find
I
it.
think goopy also works.
How many shirts you like?
No, I'm too dumb. Should that were new.
Yeah, 527. Hey, there's coagulation.
Yeah, that was what I said. I said like,
Oh, that's what
I said coagulating. I just made up a word. It's not a real word. I don't think so. At least.
I'm interested to read that. I don't know if I ever read that.
Coagulating.
The destruction of a colloid. Probably did a long time ago.
Burn it. Fire. That's cool.
Alright. So what you see in the top left corner on page 527, you should see your laser, which is essentially the Tyndall effect. And the one on the left is your solution, the one on the right is your colloid. They look very similar. What?
Right to the water cooler.
Yeah, of course. So the Tyndall effect is how you can distinguish the difference between a solution and a colloid. And what ends up happening is in a colloid, you can see a laser when it's shot through it because the particles are big enough that it scatters the light and you can see it. In the solution, the particles are not big enough to scatter the light that it hits your eyes, and so it just goes straight through. Okay, so I'm going to read starting on where it talks about colloidal dispersion. A suspension of tiny particles in some medium is called a colloidal dispersion or a colloid. The suspended particles are single large molecules or aggregates of molecules or ions ranging in size of 1 to 1,000 nanometers. Colloids are classified according to the states of the dispersed phase and the dispersing medium. And it talks about that in the table above. What stabilizes a colloid? Why do the colloids remain suspended rather than forming large aggregates and precipitating out? The answer is complicated. I love when they say that.
Makes me want to ask Kramer questions and he doesn't know or can't explain it without going 3 chapters ahead.
Well, sometimes I just don't know, and other times I just don't know.
You become confused.
There's a, well, no. I mean, science is a very complex thing, and it has very much layers to it. And there's only so
Science.
there's only so. I mean, like I don't claim to be some, physicist on the cutting edge of, learning every little detail of every little thing. I don't. And there's actually, other than the stuff I teach, there's very little I remember about college. I remember big highlights of things, but unless you use it, you lose it. That's just the way it is. Anyways, where was I? Oh yeah, the answer is complicated, but the main factor seems to be electrostatic repulsion. A colloid, like all other macroscopic substances, is electrically neutral. However, when a colloid is placed in an electric field, the dispersed particles all migrate to the same electrode and thus must all have the same charge. How is this possible? The center of a colloidal particle attracts from the medium a layer of ions, all of the same charge. This group of ions in turn attracts other layers of oppositely charged ions, as in figure 11.24. Because the it's hard to say, colloidal particles all have an outer layer of ions with the same charge, they repel each other and do not easily aggregate to form particles that are large enough to precipitate. The destruction of a colloid, or coagulation, usually can be accomplished either by heating or by adding an electrolyte. I wonder why an electrolyte would do that. Adding a charged particle to mess up the layers of ions.
Well, ions might have stronger
It's down
charges.
in the last one.
Does it say at the end? What?
Not the last one.
Oh, adding an electrolyte neutralizes the absorbed ion layers.
Oh,
Or
sorry.
adsorb, sorry, they have a typo. Adsorb.
Well, adsorb is the thing.
Oh, it is?
Yep.
Oh.
Adsorb is like coming onto the surface of a layer.
Oh, okay.
Like when gas molecules are attracted to the metal surface of something, they say it adsorbs. It doesn't absorb in, it adsorbs to the surface is what they call it. So the adsorption is when it like
Learn something every
essentially
day.
sticks to the surface.
See, Kramer, you know vocabulary. Oh, I didn't know that word, and I like to read.
Few things.
Yeah. You know your job, do it well.
Well, I tried to. Heating increases the velocities of a colloidal particle, causing them to collide with enough energy that the ion barriers are penetrated and the particles can aggregate. Because this process is repeated many times, the particle grows to the point where it settles out. Adding an electrolyte neutralizes the adsorbed ion layers. This is why clay suspended in rivers is deposited where the river reaches the ocean. Forming the delta. Delta is characteristic of large rivers like the Mississippi. The high salt content of salt water causes the colloidal clay particles to coagulate.
Oh. That's cool. I was assuming it was gonna slow down, I would assume.
What?
I would assume the clay fell out because it would just slow down.
Because it wasn't running through the.
It wasn't running through the muddy riverbank, but this makes sense too now, I guess.
The removal of soot from smoke is soot from smoke. I don't really know the difference.
So it's like the powdering that stains. Smoke is just that in the air.
Yes.
Well, so it's like the ash and the stuff that like coats your lung when you read campfire something is wrong.
Or smoke. Is another example of coagulation of a colloid. When smoke is passed through an electrostatic precipitator, the suspended solids are removed. The use of precipitators has produced an immense improvement in the air quality of heavily industrialized cities, except for China.
Okay. That's some Batman words I don't know right there. All like fancy electro.
All right. So, big picture here, what's coming ahead. It is Friday today. That means we're going to have our quiz on Tuesday.
That was the plan.
When?
That was the plan.
Was it?
Yeah.
How is that possible?
You kept saying that we were going to finish the book yesterday and it was Tuesday, like, so what are we doing?
Yeah, I was like total reading
I totally didn't catch all that?
Yeah.
So we're down.
See, I knew the future.
Well, now I have to change your plans.
So yeah, Tuesday, quiz. Then we'll move on to chapter 12.